Good morning, students. So let us continue. Today is going to be the 25th session in the E-Content series, and under coordination chemistry we are going to go ahead with crystal field theory. And in crystal field theory, today's class we are going to deal with tetrahedral symmetry. So in today's class we are going to go ahead with what is a tetrahedral symmetry in crystal field theory. Tetrahedral complexes are formed with late transition metal ions. Tetrahedral complexes are formed with the late transition ions, that is from with atomic number 27, 28, 29, 30. And some early transition elements like titanium and manganese in situations where the ligands are large. So, tetrahedral complexes are formed with the late transition metal ions and some early transition metals like titanium and manganese where the ligands are large. In these cases, the small metal ion cannot easily accommodate a coordination number higher than 4. That is, in tetrahedral, if a tetrahedral complex has to be formed, as we are moving from left to right, the size decreases, and because of which the small metal ion cannot easily accommodate a coordination number higher than 4. So complexes of tetrahedral ions and molecules are, that is, we have got tetrachlorocobaltate, tetrachloromanganate, and we are going to have with a halogen complex of titanium. So when we are going to consider the d-orbitals, the d-orbitals are going to get split up in a tetrahedral crystal field can be understood by connecting the vertices of a tetrahedron. Supposing we are going to consider this to be as a cube. If we are going to consider this to be as a cube, and we are going to we can consider at the vertices, because this is going to be a vertex, this is going to be a vertex, this is going to be a vertex, this is the vertex, and this is the vertex. So here at the vertices there are the ligands. So under the crystal field splitting in tetrahedral complexes, what do we observe is as they are going to come at the vertices, what do we observe is here we are having along the vertices, that is xy, yz and xz, which are undergoing greater repulsions, and as they are undergoing greater repulsion, their energy is going to increase. So in tetrahedral 1, the energy splitting is going to be dxy, dyz, dxz is going to have, or this is going to be the T2G, because it is going to be T2. It is going to have a higher energy, and these two, dx square minus y square and dz square, are going to have a lower energy. Here the tetrahedral metal ligand is going to lie along the body diagonals of the cube. Along the body diagonals of the cube, we are going to consider the ligand to be present. The dz square and dx square minus y square orbitals point along the Cartesian axis. These are going to point along the Cartesian axis, that is towards the face of the cube, and they have the least contact with the ligand pairs. So they are going to have a lower energy. The two orbitals form a lower energy doubly degenerate E set. It is because we are not going to use it as EG, because here it has got no center of symmetry. As it has no center of symmetry, we are simply going to write it as, or doubly degenerate simply as E set. And the dxy, dyz and dxz orbitals point at the edges of the cube and form a triply degenerate, and this is simply called as T2 set. While the T2 orbitals have more overlap with the ligand orbitals than the E set, they are still weakly interacting compared to the EG orbitals of the octahedral. When compared to the octahedral complex, they are still weakly interacting. the splitting energy in case of tetrahedral symmetry is going to be represented as delta T, and this is about 4/9, the splitting of the octahedral complex formed with the same ligands. So the splitting delta T is about 4/9, the splitting of an octahedral complex formed with the same ligands. For 3D elements, delta T is thus small compared to the pairing energy and the tetrahedral complexes. Their tetrahedral complexes are always going to have high spin. Here, what do we observe is, as the orbitals as the ligands are going to approach, first the energy is going to increase. The energy is going to increase, and they are going to, here, what happens is, it is going to decrease by the dx square minus y square and dz square in a tetrahedral field is going to have a lower energy, whereas dxy, dyz and dxz is going to have a higher energy. The G subscript, which is used in octahedral and square planar complexes, is not written here because this has no center of symmetry. Tetrahedral complexes often have vibrant colors because they lack center of symmetry. That is, the DD transition are formed. Because of the low energy transition is allowed. These complexes typically absorb the visible range and have extinction coefficients that are 1 to 2 orders of magnitude higher than those corresponding to the octahedral complex. For example, if we are just going to consider a complex, of cobalt here, what do we observe is that is in hydrated form. If it gets hydrated and in the form of a ligand, what happens is, in tetracobaltate 2, it is going to have a tetrahedral structure, and this is going to be deep blue in color. Whereas if it is going to be in an octahedral one, if the same thing, it is going to be in an octahedral one, that is in anhydrous one. If it is going to be in an octahedral one, it is going to be light pink in color. So we can tell tetrahedral complexes often have vibrant colors because they lack center of symmetry, and that forms a DD transition. Because of the low energy transition is allowed, these complexes typically absorb the visible range and have extinction coefficient that are 1 to 2 order of magnitude that are higher than those of corresponding octahedral complex. And one such example is going to be a dryite, which contains particles that are colorless anhydrous calcium sulfate gypsum that absorbs moisture from the gas. The indicated dye, that is dryite, is cobalt 2 chloride. This is going to be a cobalt 2 chloride, which is light pink when it is going to be wet. When it is going to be wet, it is going to have a octahedral structure, and when it is going to lose the hydration, it is going to be a tetrahedral one, and this is going to be a deep blue in color. So this is all about in today's class. Thank you, students.